The topic of today's lecture is Enantiotopic and Diastereotopic atoms, groups, and phases. So, we will divide this topic actually into two subtopics. First subtopic will be the Enantiotopic and Diastereotopic atoms and groups. So, we will study it under the heading of prochirality at SP3 hybridized centers. So, I will define this term, what is prochirality, and the second subsection will be anisotropic and diastereotopic phases. So the means we will deal it under prochirality at SP2 hybridized centers. So these are two subtopics, means anisotropic and diastereotopic atoms and groups. Second, anisotropic and diastereotopic phases. So let's start by subsection A, that is anisotropic and diastereotopic atoms and groups. An atom which is attached to two identical ligands and two other different ligands. For example, a compound of the type CAABC. C is the central carbon. AA means two similar groups are attached. BC which are different. If you have a molecule of the formula CAABC, in which central carbon is attached to two similar atoms or ligands and two dissimilar atoms or ligands, such a center is known as a prochiral center, and the molecule is said to possess prochirality. The molecule is said to possess prochirality. Why it's known as prochiral? Because this molecule has a potential to be converted into a chiral center in a single step. So that's why it's known as the prochiral. Means prochiral is a center or a molecule which can be converted into a chiral center by one step reaction. And the two identical ligands which we mentioned in the previous slide, the two identical ligands attached to a prochiral center are said to be enantiotopic. They are said to be enantiotopic if replacement of each in turn by a different achiral ligand, which is also different from other ligands attached to the prochiral center, gives enantiomers. So what are enantiotopic ligands, or what are enantiotopic groups? The two identical ligands, they are said to be enantiotopic, the two identical ligands which are attached to a prochiral center. We will call them enantiotopic only if replacement of each in turn by a different achiral ligand. So if we replace these two similar ligands by a different achiral ligand in series wise, first we'll replace first group, and in second step we will replace the second group. And by replacing these groups one by one, if this replacement of these two groups one by one gives enantiomers, then we call such ligands, which we call such groups, or we call such atoms as enantiotopic atoms or enantiotopic groups. So if the replacement gives enantiomers, we will call them as enantiotopic groups or enantiotopic atoms. We'll see this in detail. For example, take the simple example of ethanol. Replacing one of the CH2 hydrogens by a group Z, suppose it's any group, if we replace these two hydrogens by a group Z, it will give two enantiomers, two different hydrogens. If they are replaced one by one, they will give you two different enantiomers. So we will say that the CH2 hydrogens in ethanol are enantiotopic. we will call them as anisotropic hydrogens. Why? Because their replacement by any group Z gives one by one gives enantiomers. For example, this is the structure. This is the structure of ethanol, CH3, CH2, OH. And these two hydrogens which we are talking about, if we replace these two hydrogens one by one, this replacement creates this kind of stereoisomer. And this replacement means in this step we have replaced this uh, you know we have replaced this hydrogen, and in this step we have replaced this hydrogen. So replacing these two hydrogens one by one gives enantiomers. It means this compound, let me mark it. It means this stereoisomer and this stereoisomer, they are enantiomers to each other. Means if this is R isomer, this has to be S isomer. This will be an S isomer. Means these two are enantiomers to each other. So we'll call the ethanol as a prochiral molecule. So it will be known as, ethanol will be called as prochiral molecule. Why? Because this prochiral molecule has enantiotopic hydrogens. A prochiral molecule means it has the potential to be converted into a chiral molecule in a single step. So that's why it's known as the prochiral center. We will call it as a prochiral center. And this prochiral center here has enantiotopic hydrogens. Why it has enantiotopic hydrogens? Because when we replaced them one by one, these two hydrogen, when we replaced them one by one, we obtained two different stereoisomers which are enantiomers to each other. So these protons are known as enantiotopic protons. So these two hydrogens here, they are known as enantiotopic hydrogens. We'll call them as enantiotopic hydrogens since their replacement by a group Z gives enantiomers. Very simple. So this molecule will be known as prochiral molecule because it can be converted into a chiral molecule in a single step. It's known as a prochiral center. There is something called a prochiral center. So prochiral center is a center which will be converted into a chiral center in two steps, right? So you have to note here the X atoms are groups of any molecule of the form CX2WY, where X2 are similar groups, W and Y they are different groups. They are always enantiotopic if neither W nor Y is chiral. So you have to bear this thing in mind also, that a compound of this type CX2WY, these two uh, atoms, X2 atoms, are always enantiotopic if neither of these, neither W nor Y, are themselves chiral. If they are chiral, then we will use a different term there. We'll call them as diastereotopic. So for enantiotopic, this W and Y have to be these two. They have to be a chiral. So these have to be a chiral. Then these X2 will be, these atoms will be known as enantiotopic. We'll call them as enantiotopic. So the term prochiral is used for a compound or group that has two enantiotopic atoms or groups. So any molecule, any compound that has enantiotopic atoms or enantiotopic groups is known as a prochiral molecule. So ethanol is a prochiral molecule. Why? Because it has two enantiotopic hydrogen. So we'll call ethanol as a prochiral molecule. So a prochiral molecule can be converted from achiral to chiral in a single step. This thing I have already told you. So this is ethanol. This is ethanol molecule. So in a single step, we can easily convert it into an optically active. This is chiral molecule. This is optically active. This is a prochiral molecule. Remember, a prochiral molecule is optically inactive, not optically active. So it is a prochiral molecule is optically inactive. It's very important. It's known as prochiral, but it's not optically active because the central carbon, this carbon is attached to two similar atoms. So note that that atom or group X that leads to R compound is called as a pro R, while the other is known as a pro S. So this nomenclature you have to keep in mind that the two atoms or two groups in a prochiral molecule, we call them as pro R or pro S depending on what they form. So if by replacing, suppose you have an atom in a molecule, in a prochiral molecule, by replacing that atom, if you obtain an R enantiomer, so we'll call this group as pro R. And if by replacing that group, if we get the S enantiomer, we will call it as pro S. So in this molecule here, in this molecule, this H2 is known as pro R. This H1 is known as, this proton is known as pro R because its replacement will give an R enantiomer, and this H2 here is known as pro S because its replacement will give an S enantiomer. So this is known, these groups are known as pro R or pro S groups are atoms. Now it was about anisotropic atoms and groups. Now we move to second topic of subtopic, that is diastereotopic atoms or groups. So when two atoms or groups in a molecule are in such position such that replacing each of them in turn by a group Z gives rise to diastereomers, such atoms or groups are known as diastereotopic atoms or diastereotopic groups. So it's the term is pretty much clear. So when two atoms or groups in a molecule, they are in such a position such that replacing each of them by a group, any group Z, it can be any group, this replacement of these two groups, in turn, stepwise, in different steps, if if by replacing these groups by a group Z gives rise to diastereomers, then those atoms or those groups will be known as diastereotopic. They will be called as diastereotopic. Example is the CH2 groups of 2-chlorobutane. These two CH2, these two hydrogens in 2-chlorobutane, they are known as diastereotopic. Other examples of diastereotopic include include this molecule. Take the example of this molecule. These two hydrogens here, this hydrogen and this hydrogen here. We'll see what these hydrogens will, can we call them as anisotropic, or can we call them as diastereotopic? Should we call them as anisotropic or diastereotopic? Let us see. If HA is replaced by, in this step, if HA, this proton, is replaced by D, we get this compound, this stereoisomer, right? And in second step, if this HB is replaced, by a group D, you get this stereoisomer. right? And in replacing these two hydrogens, Ha and Hb, what you get these two compounds, stereoisomers. You get these two stereoisomers. And if you correlate these two stereoisomers, means if you correlate compound number 3 and compound number 2, you will see that these stereoisomers are actually diastereomers to each other. Why? Because these stereoisomers have same configuration at one chiral center and opposite configuration at other chiral center. So you can see this is carbon number 2 and this is carbon number 3. At carbon number 2 they have opposite configuration, while as at carbon number 3 they have similar configuration, right? No, at carbon number 2 they have similar configuration, while as at carbon number 3 they have opposite configuration. So means 2 and 3, this molecule, this stereoisomer and this stereoisomer, they are diastereomers to each other. How they have been formed? They have been formed, these stereoisomers, means 2 and 3 have been formed by replacing these hydrogens Ha and Hb. So such atoms or such groups or such hydrogens, which when replaced by a group D, they give rise to diastereomers one by one. Such atoms or such groups are known as diastereotopic atoms or diastereotopic groups. So Ha and Hb are known as diastereotopic atoms, or they are known as diastereotopic groups. So in compound 1, means this compound C2 is a stereogenic center. This one, it's also a chiral center, already a chiral center. Mark my words, when we talk about diastereotopic atoms or diastereotopic groups, a molecule already has a chiral center. So if a molecule already has a chiral center, then it can have diastereotopic atoms or groups. Otherwise, it cannot have diastereotopic atoms or groups. This is very important. So in compound 1, C2 is a stereogenic center, and if we replace separately Ha with D and then Hb with D, we obtain 2 and 3 respectively. The compounds 2 and 3, I have already told you, that diastereomers, so the H and Hb will be known as diastereotopic. We'll call them as diastereotopic. Now the difference between anisotropic and diastereotopic protons, and they can be differentiated using NMR. While anisotropic protons or groups are chemically equivalent, meaning that they are indistinguishable in NMR experiment, except when chiral solvents are used, in which case anisotropic protons give different peaks. See how we differentiate these anisotropic and diastereotopic atoms. They are chemically equivalent, and any protons or any groups which are chemically equivalent, they are indistinguishable. They give a single peak, they don't give different peaks. But this is only the case when we use achiral solvents. If we use chiral solvents in them, these protons, they can have different chemical shifts. That means they can give different peaks, and it means that anisotropic protons are isochronous. We use the term isochronous, meaning that these hydrogens are indistinguishable in NMR and give a single peak. So they are isochronous, means they cannot be distinguished in NMR if we use an achiral solvent. So they give a single peak. That's why they are known as isochronous. However, diastereotopic protons are groups. They are anisochronous, meaning that they are distinguishable in an NMR and they have different chemical shifts, and these protons react at different rates. Means diastereotopic protons, they react at different rates, while as anisotropic protons, they react at same rates, except that if you are using some chiral reagent. If you are using chiral reagent, then even anisotropic protons or anisotropic groups, they react at different rates. This was about prochirality at sp3 hybridized carbon. So why we call that at prochirality at sp3 hybridized carbon? Reason is this, this prochirality in this molecule, you can see that this uh, center here, this carbon here, it's sp3 hybridized, and it's a prochiral center. It's a prochiral center. That's why we gave it a heading, prochirality at sp3 hybridized carbon. So an sp3 hybridized carbon can have prochiral atoms or prochiral groups. It cannot have prochiral faces, right? That's why we gave it this heading, sp3 hybridized prochiral center. Now we move to another topic, which is, you know which is anisotropic and diastereotopic phases. Now we will talk about phases. Means prochirality at sp2 hybridized carbon. So far we dealt with sp3 hybridized carbon. So first we'll see what are anisotropic phases, right? The idea of prochirality can also be applied to phases of trigonal centers in suitable molecules. Some molecules which have sp3 hybridization, they have trigonal centers, like aldehydes, like ketones. They have trigonal centers, sp3 hybridized carbon. And this concept of prochirality can be applied to these molecules also, right? For example, the faces of a trigonal atom or a double bond. A double bond can also have different faces, right? Because it is sp3 hybridized. The faces of a trigonal atom or a double bond are called enantiotopic. We call them as enantiotopic if addition of an achiral reagent, if we add an achiral reagent to one or the other phase, gives enantiomers. So what are enantiotopic phases? Enantiotopic phases are those phases, if we add some achiral reagent to these phases one by one in separate steps, and in doing so, if adding an achiral reagent to the different phases gives enantiomers, then such phases are known as, we'll call those phases as enantiotopic phases, right? So chirality can also be generated by addition to an enantiotopic phase. So a chiral molecule can also be generated from a molecule which has enantiotopic phases, right? Similar is the case with sp3 hybridized. There also we saw, these anisotropic atoms or groups, they can give rise to chiral centers. Same is the case with, prochiral phases. They can also give rise to chiral molecules or chiral centers. Example is this acetaldehyde. You see, this molecule, it has two phases. This carbon is sp2 hybridized carbon, right? It has two phases. This is one phase and this is another phase, and we call these phases as re phase or C phase. They are known as re phase or C phase. Re phase means if the orientation is this one, the numbering system gives number 1 to oxygen, number 2 to methyl, number 3 to hydrogen. And if you draw an arrow from oxygen to methyl to hydrogen, you are going clockwise. Clockwise means R, but we don't call it as R. While a molecule which has phases, we use a different terminology. We use Re and C. So it has Re phase, RE. It's known as Re phase, and this one, it is known as C phase. So they are different phases, right? So when we treat them with HCN, suppose CN ligand, it leads to the formation of the CN. It can attack this molecule from this phase, or it can attack this molecule from this phase. right? These are two different phases. In doing so, when it goes from one phase, it gives rise to this molecule, this stereoisomer, and when it attacks from other phase, it gives rise to this stereoisomer. And if you see these two stereoisomers, they are enantiomers to each other, right? So we call these phases as enantiotopic phases. Why? We say that this molecule has enantiotopic phases because by adding this Cn negative to two of these phases one by one, it gave rise to enantiomers. So we call such phases as enantiotopic phases. Such phases are known as enantiotopic phases, right? So two different phases of an sp3 hybridized carbon. It has two different phases, and addition to these two phases separately gives enantiomers. That is why they are known as enantiotopic phases, because addition to these two phases separately gives enantiomers. That's why they are known as enantiotopic phases. On the other hand, if you take the example of this molecule, this is acetone, CH3CO, CH3. Acetone has identical phases, means both of these phases, this phase or this phase, they are same. And when we react this molecule with HCN, it will give rise to achiral products, and it is said to have homotopic phases. So this molecule has homotopic phases because by addition of Cn negative to these two phases in this molecule will give rise to the same molecule, this one. So same molecule will be formed. That's why these phases will be known as homotopic phases. So this molecule which is formed, it will be achiral, right? Because central carbon, this carbon, it is attached to two similar groups, that is methyl groups. So such phases are known as homotopic phases. What are diastereotopic phases? It is also possible for molecules to possess diastereotopic phases. So for diastereotopic phases, you have to keep one thing in mind. Like in case of diastereotopic atoms or groups, in case of diastereotopic phases, a molecule must already have a chiral center. It must already have a chiral, at least one chiral center. Then it can have diastereotopic phases, right? Examples include some cyclic ketones as well as cyclic molecules like camphor. See, these kinds of molecules already have a one or more chiral centers, stereogenic centers. This is I already told you. This is very important. For diastereotopic atoms or phases, a molecule must already have a chiral center. Take the example of this molecule. You have a chiral center here. This is a chiral center here, right? And this is an sp2 hybridized carbon. So this sp2 hybridized carbon will have phases, right? There are two phases to it. This is one phase of this, and this is another phase of this. This Cn can react with this C double bond O from two phases. This is one phase and this is another phase, right? So when this Cn negative reacts with two phases of this molecule, it gives rise to one compound. This is one stereoisomer and this is another stereoisomer. These two stereoisomers are formed when the Cn negative attacks this C double bond O here from two different phases. And if you see the relationship between this one stereoisomer and this stereoisomer, you see uh, these two molecules here, they are diastereomers to each other. Why? Because they have same configuration at one carbon, means this carbon has same configuration, while as this carbon has opposite configuration. So I already told you molecules with two chiral centers or more chiral centers, which which resemble at which resemble in configuration at one chiral center and have opposite configuration at other chiral center. They are known as diastereomers. So such phases, this molecule is said to have diastereotopic phases, because by addition to these phases, by addition to these phases, one by one, stepwise, gives rise to diastereomer. So this molecule is said to have diastereotopic phases. So this is another example. This molecule can also have diastereotopic phases. This is one phase to it, and this is another phase to it. You can carry out its reaction yourself, suppose by reacting it with Cn negative, and you can easily see different diastereomers are formed. This can be a homework to you. You can treat it as a homework. You can try these molecules, how different stereoisomers will be formed, how different diastereomers will be formed from this camphor. So a carbonyl carbon located in the same molecule as has a stereogenic center is diastereotopic. So this carbonyl carbon here, it is said to be diastereotopic because it is present in a molecule which already has a stereogenic center. And while is the stereogenic center, this is the stereogenic center here, this is the stereogenic center here, and this carbon is adjacent to this stereogenic center. So reagents will approach one phase of such a carbonyl carbon more easily than the other, then they approach the other. So these two phases of this molecule, they'll be approached by the reagent in different capacities. That's why they give rise to different diastereomers. So this is all for today's lecture. We'll be back with another lecture of stereochemistry. Till then, goodbye, take care.